Inductors and Inductance, Part 2 of 2. In this presentation, we're going to be looking at some of the calculations involved for inductors in DC circuits. We're going to investigate a bit and expand on inductive kick, and we're going to end with some discussion on mutual induction. So first, let's just review what happens with an inductor as we are energizing a circuit. When we energize a circuit, and we're going to energize a circuit starting with the left-hand conductor here, counter EMF is going to be generated on the second turn of the coil due to the expansion of magnetic lines of flux. And this counter EMF will cause a current to flow in the opposite direction, which will oppose the initial source current. And what this will have an effect of is slowing the amount of, or increasing the time it takes for the source current to reach its peak value. Once the circuit is fully energized in a DC system, no counter EMF will be produced. And that's because the current will have reached a steady state value. And remember, the definition of inductance is that it will have an effect when there is a change in current flow rate. When the circuit is de-energized, there is a change in current flow, a collapsing magnetic field, which will cause an increase in voltage. And so again, the circuit will be increasing the length of time that it takes for the circuit to reach zero. An excellent example of this is a paddle wheel, and I encourage you to take a look at the video on the engineering mindset from YouTube. So let's take a look at these two different circuits that we have on the screen. We've got a resistive DC circuit, and we've got a current and time graph here showing when the switch is closed, current immediately reaches its full peak value established by Ohm's law, and then it stays at this value until the switch is opened, at which point it drops to zero immediately. That would be in a typical resistive DC circuit. What happens in a inductive DC circuit? So I've got a coil of wire, which is an inductor, and a resistor here. They're both connected together in this DC circuit. Well, now what happens is the length of time that it takes to reach this steady state value of current is increased. It takes longer. And then finally, once it reaches that steady state, it's unwavering. It is direct, it's constant, it doesn't change, much the same as up here. This one here, you'll notice the magnitude of it is about proportional to the magnitude of this one. And that's because the amount of current that flows will only be calculated by the amount of resistance. So if this resistor here allowed 5 amps of current to flow, and we took the same resistor and put it down here, well, guess what? The total amount of steady state current will again be 5 amps. The difference again establishes itself when the switch is opened. Watch, it takes longer for the current value to reach zero. And some funny things happen here because of the coil. Obviously, we don't have a straight vertical line for establishing current and a vertical line dropping to zero immediately. It takes time. And so once time is entered into the equation, we have some other calculations that we can do. Let's look at this specific point here. There's some odd things that happen when a switch is opened on a DC circuit. At that point there will be something called an inductive kick, and it's not really shown on the graph because it is such a short time period. But we're going to take a look at how we calculate it and why it happens. So let's take a look at this overall graph. I've divided it into a few different sections, same sort of idea of time and current. We've got switch being closed here, and then this second dotted line, kind of a wavy line, it should be more linear, smoother, I suppose. This line here is indicating where we have reached our steady state value of current. And then you'll notice here, switch is opened. And notice that we have a spike, and then it drops down. So something interesting will take place at that time portion. So first thing we need to know is something to do with time. How long in seconds will it take for the current to start from zero and finally reach its peak or steady state value in the DC circuit? That time in a resistive inductive circuit is calculated by taking the henries, dividing it by the resistance, and then multiplying it by 5. Now, why 5? Well, this is an example of a exponential curve or a logarithmic relationship. And the significance of that is that universally, this type of increase in any type of situation can be divided into 5 equal time values. And those time values can have percentages fixed to them. So the seconds total time is equal to 5 times the length, the induction time divided by the resistance. This is what a exponential curve typically looks like. This one is showing percent of final voltage, but it really doesn't matter what we're discussing. An exponential curve is one in which the points equally divided into 5 will have specific percentages affixed to them. It doesn't matter if we're talking electrical, mechanical, astrophysics, gravity, whatever. Each one of these time constants, 1, 2, 3, 4, 5, will have a percentage. At the first time constant, the current will have reached 63% of the steady state value. At the second time constant, it will have reached 86.3%. At the third time constant, 94.93. At the fourth, 98.12. And at the fifth, 99.3%. Now, the significance of these percentages is that they are the same for every single situation. And so there's a number of different ways that we can go about calculating what the current will be at each of these specific time periods, which I'll show in a different presentation. Notice 99.3. An exponential curve simply means that it won't actually reach 100%. It'll still keep rising. 99.3, 99.8, 99.9998, 99.9999987. It'll continually get larger and larger, but the definition of exponential graph or curve is that it won't actually reach 100%. And so although it says 99.3% is steady state value, we just kind of assume it's reached its target value by that point. Those 5 different, or not different, but 5 equal time spaces over the entire exponential curve are called time constants. The time constant here is equal to the inductance divided by the resistance. So we have 5 time constants, and we can calculate the seconds of one time constant to get one chunk of seconds or time that it would take. And then we multiply it by 5, we get the total time it would take for the inductor to allow for the current to reach its steady state value. What else is going to happen in the inductor? Well, once it's reached this steady state value, the inductor is going to be effectively completely charged up, as in it is storing an exceptional amount of energy in joules. And so the energy in joules is calculated with this equation down here. W is equal to 0.5 times induction times I squared. The W represents energy in joules, so it's a little bit different. It doesn't actually represent watts. L is the inductance, and I is the current flowing through the inductor. It's the steady state current value. So we can calculate how much energy is stored by the inductor when it has reached its steady state value. And that's important for the last item here. Now, I've included it on this graph here because really, if we were to calculate the voltage that is going to be produced here, there's going to be a really high spike in current, which would cause a high spike in voltage. And the energy that was stored in the inductor as joules of electromagnetic energy will be released when the switch is opened. Now that voltage can be calculated with this equation here, negative L I over T. And this is commonly known as a voltage kick. A voltage kick is something that is going to be a property that we want to try to limit. All right, inductive voltage kick. So what we're going to look at is sort of 3 different steps of a inductor in a DC circuit. Got a little stickman dude here, and he's going to operate the switch, DC, inductor, switch, open. So inductor is de-energized, there's no current flow, and this is at the very beginning when we first connect the whole circuit up. So what's going to happen? We are going to close the switch. So there's my little stickman dude, and he has closed the switch, and what's happened? Well, now we have current flow in the circuit, and that current flow we know is going to be based, the time period, on the amount of inductance in the inductor and the resistance of the inductor or the wires. The inductor is going to energize, current will flow, slowly increasing until finally the current has reached its steady state value. At that point, we can assume that there will be a significant quantity of energy stored in the inductor through electromagnetic bonds in the form of joules. So once we open the circuit, we're going to get an extremely high voltage. And that voltage is going to be all of the joules of energy being discharged from the inductor because of the rate of current flow changing so quickly down to 0. So that voltage will be impressed across the item that opened the circuit. And so this would be known as the inductive kick. It's a high momentary voltage arc across the switch. And that can cause significant damage to equipment, as well as cause injury or death if it was large enough. We can calculate what the voltage will be, the inductive kick, with this equation. So E, the voltage, is equal to negative L, so that's the inductance in henries, multiplied by original current minus the new current in amps, divided by T, which is the time in seconds. So essentially, what we're doing is we are calculating the voltage based on how quickly the current drops. The original current minus the new current in amps, original current was, say, 5 amps, minus the new current, which is, let's say, 0 amps. That means 5 amps would be used for the calculation. There are a couple of different ways we can suppress the voltage kick, and very often you will see things like this, a freewheeling diode being put in place. It's in parallel with the inductor, and a diode will only conduct in one direction. And so what that means is that when it's connected in this manner, current will not flow through the inductor because it's reverse biased. When you open the switch, current will flow the opposite direction through the inductor, or rather through the diode from the inductor, and that will conduct or cause the diode to close or to, what's the word I'm looking for? Conduct, so current will flow through it. And that will provide a discharge path through the inductor itself. It's a little short circuit. We'll put diodes in places where that inductive kick could cause damage to electrical equipment. And a really good example of that is when we have relays, DC relays, that are used along with PLCs, or programmable logic controllers. A PLC is very expensive, and when we are controlling a DC coil of a relay with a PLC card, we don't want the inductive kick to fry the PLC card when it opens or closes, as in energizes and de-energizes the DC coil. So you'll see that quite often. Mutual induction. Well, let's take a look now at an inductor and what happens when we have two different coils of wire. So remember, we've looked at this. This is the initial coil and we know it has inductance. What if we had a second coil right beside it? Remember, as the current flow increases, we're going to get this increasing or expanding magnetic flux. And what will happen? There's going to be cutting of magnetic flux across the conductors of this secondary winding. And so that secondary winding would then have a voltage induced onto it, and of course, some current that would flow through it. Now, what will happen in a typical installation is based on Lenz's law and what we can expect with direct current. So what I have here is a DC source with a DC coil, and it's reached its steady state value. Over here, I have a secondary coil, and I have a little voltmeter on it to indicate negative or positive. When I bring it close, you'll notice that the needle moves a little bit. So I'm going to move it away and move it close. Move it away, move it close. And what you're going to notice is that there is a deflection of the meter. I'm going to increase number of loops so we can see it better. When I move it one direction, the needle moves one way. But when I move it the other direction, the needle moves the opposite direction. And so what that means is that the voltage produced is in an opposite direction or opposite polarity. Now, when we put a DC source on with a secondary coil, it doesn't really make a true transformer, because if I were to put this back to a light bulb, when I move the DC source, I get a voltage induced into the secondary coil. But if I just put it there and leave it, the light doesn't stay on. And so really that wouldn't make a very efficient transformer in the way that we would see with an AC circuit. Instead, when we use DC with two separate coils, we're using it for a different purpose. Just for your own information, that animation was Faraday's electromagnetic lab, and it was through the University of Colorado physics department. They have a vast array of physics simulations available free of charge. So in a DC circuit, when we energize one coil, electromagnetic flux will flow, and it will, when expanding, break across the secondary coil. Closing the switch will cause a momentary voltage to appear across the secondary coil. Now, opening the switch will cause a very interesting phenomenon. We know that there's going to be a high value of voltage across the switch due to the inductance, and that value of voltage is due to an expansion of magnetic lines of flux. So if they expand when we open the switch, that means the expansion will also break across these conductors. And what that will cause, depending on how many loops we have of wire here, this can cause a significant high voltage across the secondary coil. And this is probably the most applicable application that we see DC inductive circuits used for. So think of examples like a taser. A taser is not a constant voltage, but it's a tick, 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 tick. And that tick, tick, tick is actually a DC circuit being opened at a very high frequency or repetitive nature. Same with a cattle prod, tick, tick, tick. Electric cattle fence. If you've ever held on to a cattle fence before at a farm, you'll know that it's not a constant voltage, it's a momentary burst of voltage. Again, it's accomplished through use of an inductive DC circuit. And finally, let's just consider engine ignition sparks. You have a spark plug, and in a gasoline engine, you need that spark in order to ignite the fuel. So we have things like this, right? Two separate coils, primary and secondary. We have an extremely high voltage that's produced so high that it can arc through air between this tiny point here and the band on the side. And that spark ignites the gasoline. And here's just a pictorial image of what would be seen with auto ignition systems. Not something that we're going to spend a significant time investigating. In an AC circuit, something quite different happens. When I close the switch, this electromagnetic flux is expanding and contracting 60 times every second. That means there's constant relative motion between flux and conductor. And so what that will cause is a constant voltage to appear across the secondary coil. So let's look at our animation again. Let's change this to an AC source. Notice that the light almost appears as though it's constant in its illumination. If I increase the frequency, as in how many cycles per second we get, at a certain point, we will no longer be able to visually see that the light is blinking. And so this, what we see here, this is an example of a transformer, and we're going to investigate that further later on within the program. But a transformer will take an AC source and, depending on how many loops I have on the secondary, provide a different voltage to a load. I hope you enjoyed this second presentation on inductance and inductors, and hopefully it clarified a few different calculations and the operational features that you would expect to see with a DC circuit and inductors.